I got a handful of emails from folks who missed the first quiz. And then, so for missing the first quiz, don't stress about it. And I know that's easier said than done because I'm not getting a grade on it. But everyone's going to get at least 2 drops. Probably there's going to be 3 drops over the course of the semester. So that miss, just consider that to be one that's ultimately going to be dropped. So it's not going to impact your grade substantially. The next thing was there. The next thing was that there were a handful of people who got mixed up on the timeline. And I mentioned that, hey, the quizzes are going to go live at 11 a.m. and then they'll close 48 hours later. What I have done in response to that, or what I've decided to do was, you know what? I understand where you're coming from. A quiz closing at 11 a.m. is a little confusing. So what I'm going to do is instead extend that. So every quiz will be ending at 11 p.m. rather than 11 a.m. So totally, you're going to have about 60 hours to do those quizzes. Now that's going to be implemented starting right now with, I believe it's quiz 2 and quiz 3. Quiz 2 is the Proctorio quiz. I mentioned the Proctorio quiz. If you get prompted for an access code, then you probably need to try a different web browser. And if trying a different web browser doesn't resolve the issue, then what I recommend doing is, try a different computer if you can, or contact ITAC at txstate.edu. That's our tech support on campus, and I'm not sharing my screen, so the information that I just wrote is not being seen by y'all, but instead my faces. But now it is being shared. So ITAC at txstate.edu. If you encounter any tech issue, you can email them or you can call them. And if I'm like 99% sure that this is their number, 512-245. And then 4822. I'm like 98 to 99% sure that's the number. So if you encounter any tech issues, give them a call. They're very good about, basically asking, oh, what kind of computer are you using? What browser are you using? And helping you kind of sift through and identify what the issue that you're encountering is. They're very helpful. So they can help you with the Proctorio issue. But like I said, if you're prompted for a access code, that means more than likely that Proctorio is not being opened. And so that's just it's not being opened. And so so it's like a pop-up blocker or something like that. So at any rate, those were 2 things that I wanted to bring up and make sure that you were familiar with. That phone number, and then the quizzes you'll have until 11 p.m. tonight for the Proctorio one, and then for, I believe it's quiz 3. So at any rate, we'll go ahead and get started. Today, I'm excited to talk to you guys about atomic structure and electrons in atoms. Okay, so the proctored one, yeah, absolutely. You can use notes on the proctored one. So yeah, no big deal there. Yes, absolutely. Okay, next up. And all of your quizzes, anything that's labeled a quiz, use your notes. They are open item. Exams are going to be a different story. But yeah, quizzes, remember I mentioned quizzes are basically like homework for all intents and purposes. So, okay, cool. So a very, very long time ago, there are people who are like, oh, there's this, I think everything's made up of cells. I think everything's made up of atoms. Every single material, whether it's this green piece of fabric behind me or my shirt or my face, anything and everything is made up of atoms. That's the smallest possible thing. And then somewhere along the way, someone was like, but what if there's something smaller than an atom? And through kind of trial and error, that's how people came up with the subatomic particles, the protons and the neutrons and the electrons. So historically, this is like our old model of an atom, or our idea of an atom. Then someone said, okay, well, I think that there's these subatomic particles and they have different charges. Some of them are negatively charged, some of them are positively charged, and they came up with this model shown here. This was referred to as the plum pudding model. Now, I believe that plum pudding is a food that is eaten, I believe it's in England. Um, I have never had plum pudding, but my understanding of what plum pudding is that you have, this tray of pudding. I'm going to draw it as a square, and then randomly distributed throughout it, there are chunks of plums. Okay. So they're kind of everywhere. There's no organization to those plums. Now, the plums in this case, in this model, the plums represent the electrons. And so the idea was that, okay, well, this plum pudding has negatively charged things all over the place. So if this is an atom, then that atom has a bunch of negative charges, but there's no organization to them. Give me a thumbs up if that makes sense. Okay, I got some thumbs up. I gotta say, I always like it whenever I ask for a thumbs up and then some people just go thumbs up in the camera. Works just as well. I can see a few people here. So we've got them randomly positioned. That was an initial, or that was like an old idea of what an atom looked like. Then there was a guy by the name of Ernest Rutherford. Ernest Rutherford, what he did was he wanted to find out a little bit more information. And so he had this experiment that was seeking to basically prove or disprove the plum pudding model. Okay. And so what he did was he came to this conclusion. He said, all right, well, what I am going to do is I'm going to get a piece of gold foil and I am going to shoot negative charges at this gold foil. And then I'm going to have a detector. So this semicircle that I just drew is the detector. And essentially what he said was, okay, the plum pudding model will be true if these negative charges basically kind of go straight through in a simple pattern. Okay. And he said, if that's the case, then I will detect these negative charges in one portion of in one portion of this semicircle. That was his contention. That was his idea. And he was like, these negative charges, they're everywhere. And so if I shoot negative charges through, they'll basically kind of go straight through an atom. Now, that was one idea. The alternative idea was that, well, if these negative charges have some organization to them and they're not just randomly positioned, then there will be some negative charges that I shoot at the gold foil that will ricochet and they will deflect. And so I will detect them absolutely everywhere. So it was this idea of, well, I'm going to find the question basically was answering to prove or disprove the plum pudding model is where will I detect, the I here is Ernest Rutherford, where will I detect my alpha particles? That was the question that he was asking. And what I want you to take away from this is that Ernest Rutherford, so I'm just going to label it as E. Rutherford, what he did ultimately was disproved I'm going to label it as PPM, the plum pudding model. And I'm going to put this PPM. He disproved the plum pudding model. So your takeaway from this is that Ernest Rutherford used gold foil to disprove the plum pudding model. Now, what his plum pudding model, or disproving the plum pudding model, what it also did was it supported a model. I'm going to jog back a couple slides, like this, a model for the atom that looked like this, where you have a nucleus. And that nucleus has protons and neutrons. So protons being our positively charged subatomic particles, and then we have this, like, all of our positive charges are at the exact center of an atom, and then our negative charges are outside in kind of a random positioning where there's some order to them. So you can basically say that Ernest Rutherford is responsible for proving the kind of existence or the idea of a nucleus. So the nucleus is, you can attribute it to Ernest Rutherford. He kind of supported that. Now, we have our subatomic particles: protons, neutrons, and electrons. Protons have a charge that's positive. Neutrons have a charge that is 0. I always like to think about neutron and they're neutral. Neutrons are neutral charge-wise. Then the last of our subatomic particles are electrons with a -1 charge. Now, the positioning of our subatomic particles is that protons and neutrons are found in the nucleus. They have mass, and so basically an atom's mass comes from the mass of a proton and a neutron. Electrons effectively have no mass, but they have a negative charge. Now, we can use this information, numbers of protons and neutrons, for putting together information on the periodic table. So what we're talking about today is going to be helpful in our next meeting, in our next lecture, and the one on Friday, where we talk about the periodic table and atoms and how they're displayed on the periodic table. So we have 3 subatomic particles. I always like to think about subatomic being lower than or smaller than an atom. You have protons with 1 mass unit, or with a mass of 1, neutrons with 1 mass unit, and then electrons with 0 mass units. So as a little bit of an exercise, I always like to think about, let's say that we made an atom. And let's go with P, N, and E. Protons, neutrons, and electrons. If you had something that was made up of 3 protons, 2 neutrons, and 5 electrons. Okay, so this is an atom. Let's call it atom A. Now let's talk about atom A. What's the charge of atom A? And then what's the mass of atom A? Now, if anyone wants to add to the chat what the charge of atom A is, go ahead and do that now. -2. Well done. That's absolutely right. Okay. Next up, what about the mass of atom A? Fantastic. Okay. So then if I wanted atom A to have a neutral charge, I could probably do that at least two different ways that I can think of. If I could make atom A neutral, add to the chat what you think I could do. And I know that this is a little bit of a lengthy answer, but go ahead and take a minute and add one of the things that you would do, or one of the possible things that you could do to it. You can add or remove subatomic particles or anything. Hunter, great response. You could subtract 2 electrons, or you could add 2 protons. So what we could do is make an atom that's, well, 5 protons, keep the number of neutrons, keep the number of electrons. I'm going to call this atom B. Now my charge for atom B, 0. What about my mass for atom B? What's the mass for atom B? Perfect. You're absolutely right, because I added something that has mass. So if I wanted to go in the other direction and make sure that my mass of atom B remained the same, then I'd remove electrons. So understanding this is super important for understanding how the different elements and atoms on the periodic table are a little bit different from one another. How when we add, or when the number of protons increases, what does that do to the mass? The number of electrons, how that increases or decreases, how that impacts the mass. Okay, so this, if there's something where I'm like, okay, take away one thing from today, it'd be this right here. Understanding that. Because, it seems like based on the number and the accuracy of responses that I got, everyone seems to have gotten that. Or most everyone kind of got that. And that's fantastic because we were just playing with like a positive or a negative number. And we did it, no problem. Problems come in whenever we start talking about elements on the periodic table. Then all of a sudden people are like, ooh, different. This is the fundamental. Keep this fundamental in mind in a couple of days when we talk about subatomic particles in the periodic table. And that will be very helpful for you. Okay, now we're going to do a quick poll. And okay, so here's, I'm going to add, it hasn't popped up yet. So in just a second, I'm going to save to library. And then I'm going to launch the poll. Okay, I've launched the poll. Which statement is true? The nucleus of an atom contains neutrons and electrons. The atomic number of an element is the number of protons in one atom. The mass number of an atom is the number of protons in the nucleus plus the number of electrons outside. And D, the number of electrons outside the nucleus is the same as the number of neutrons in the nucleus. And if you want to, I've got this PowerPoint up, or here, I'll jog back for a second. Protons equals atomic number, mass number. Okay, so that was slide 4 of this PowerPoint on the PDF if you wanted to. Give you another 10, 15 seconds. We got 56, 60 answers. Let's see if we can make 70. I think we can make 70. I need 8 people. 5 more. 4, 3, 2. Uh-oh. Uh-oh. Are you going to leave me at 68? One more. We did it. 70. Okay. And go ahead and stop this. And poll share the results. So popular answer was B. The atomic number of an element is the number of protons in one atom. And that's absolutely right. That's a good primer for the periodic table. Because this right here, whenever I say element number 18, that if I tell you element number 18, what I want you to think is, okay, that atom or an atom of that element has 18 protons in its nucleus. That's going to be a very, very helpful thing for you to be familiar with. Okay, now we'll jump ahead. So stop the share of that, close that. There we go. Now, isotopes. This is kind of a unique name. It's also the name for a minor league baseball team in Albuquerque, and it's also the minor league baseball team on the TV show The Simpsons. But an isotope or isotopes, whenever you talk about isotopes, you're really talking about two things. Because these two things are atoms with the same number of protons, but different number of neutrons. For example, this right here, that symbol X and then a number. So in this case, I took this symbol right here and kind of made it a formula, number, and then a single letter. That 1 and H, that H indicates we're talking about hydrogen. 1 indicates the mass number for that atom of hydrogen. So there are, and this sounds a little bit weird, but there's basically 1, 2, 3 different types of hydrogen. There's hydrogen with a mass of 1. There's hydrogen with a mass of 2. And then there's hydrogen with a mass of 3. These are 3 different isotopes. Now, these different isotopes also have unique names. This one is deuterium, and this one is tritium. Okay, so hydrogen is not just hydrogen. Hydrogen is this hydrogen, which we typically talk about. Hydrogen is also deuterium, and hydrogen is also tritium. So these are 3 different kinds of the exact same thing. What differs between them is the number of protons and neutrons that they have. So every hydrogen, all hydrogens, have 1 proton. Isotopes of hydrogen have, I'm going to draw a line to separate these two. Isotopes have same number of protons, but different numbers of neutrons. So deuterium, 1 proton, 1 neutron. Tritium, 1 proton, 2 neutrons. That's what makes isotopes different from one another. Now, does this say, or what does anyone notice about the number of electrons in all of these different isotopes? I'm going to erase all my ink so that everyone can see it a little bit better. What do you see about the electrons on each one of these isotopes? let me rephrase that. How many electrons does one hydrogen have? I got a direct message that they have the same. You're absolutely right. All isotopes more than likely are going to have the same number of electrons. So the only thing that varies when you're talking about isotopes is this right here. So when you think about isotopes, I strongly recommend that you think about neutrons, numbers of neutrons. Two, three different isotopes. Okay, what are we changing? We're changing the number of neutrons. The reason that that's an important thing to keep in mind is if you change the number of protons, then you're talking about a different element. So the number of protons is equal to the number or the atomic number, which is an indicator of the identity of an element. I'll jog ahead. So this is a little game that you can play with where you basically build an element. You click and drag a proton, then you click and drag a neutron, and then you drag electrons. This right here is the exact same as this table that we constructed a minute ago. You're changing an element, or you're making an element based on adding or removing protons or neutrons. That is the heart of all of this. Now, on the periodic table, you're going to see this over and over and over again, or something similar to that. You're going to see a symbol with a couple of different numbers on there. The atomic symbol is going to have a number on the upper left-hand corner, and that is going to be your mass number. That is going to tell you the number of protons and the number of neutrons. So mass number is protons plus neutrons. Atomic number, that is your number of protons. So if I wanted to kind of put this together, if I wanted to use this information and draw a nucleus with just representing protons for P and neutrons as N, I'm going to draw a nucleus of this element. How many protons do I have? Well, my atomic number tells me that I have 3. So P, P, P. Okay. Now what I want to know is how many neutrons do I have? Well, that would be this number, this 7, minus 3. So 7 minus 3 is 4. So I'm going to draw N, 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 N. 3 P's, 4 N's. That is my nucleus for the atom, or for an atom of lithium. That's all there is to that. Now, the last thing that you're going to see on a symbol like this is going to be the charge, which is the number of protons minus the number of electrons. Now, just as a little bit of a warning, if there is no number here in the upper right-hand corner, and the positioning of this is very important. If there's nothing in the upper right-hand corner, that means that the charge of that atom is 0. Does that mean it does not have charges? No. It means that it has an equal number of positive and negative charges. So that would mean something like 3 protons and 3 electrons. 3 positives, 3 negatives. Add those together and you get 0. Okay. Now, does your charge of an atom say anything about the number of neutrons? No, because neutrons are neutral. They have no charge whatsoever. Now, this right here is the periodic table, or it's an example of the periodic table. One really good web page that I like to go for a periodic table is ptable.com. I like that resource because every single element on the periodic table you can click it and it pulls up the Wikipedia page, or it pulls up like a quick summary of that element, and that can take you to the Wikipedia page for that element. Now, if we go back for a second, this symbol right here is different from these symbols. Now, why is that? Well, there's a couple of things that you need to know when you look at the periodic table okay? Each element has I guess it's no more than 2 letters that tell you the identity of that element. Ni is nickel. Ni. So nickel. That's Ni. Now, the atomic number for that is 28. What does that tell us about subatomic particles? If our atomic number is 28, does that tell us anything about the number of protons, neutrons, or electrons in an atom of nickel? It tells us our number of protons. So that's what our atomic number, that number that is a whole number. So if I asked you, and a good exam question would be, find the symbol for SB. And I'm going to ask this, go ahead and add this to the chat. How many protons does SB have? 51. I love it. Great answer. Fantastic. Great job, everyone. Okay. So then another way that I could ask that question is, you have one, let's say that we had one atom. I made an atom and it has 77 protons. What is the identity of that element? And this would be looking for the letters. IR. Perfect. Iridium. Well done, everyone. That's awesome. Great job. So those expect questions exactly like that. Given the number or given the symbol, what is the number? Okay. So now I'm going to erase this. So that, I would argue, those parts of this understanding the periodic table are pretty straightforward. Now, where it gets tricky is this number right here. So I selected palladium, PD, right here. This has an atomic mass of 106.42. Now, whenever I think about that number, that is what is known as the weighted average of all of the different isotopes of this particular element. Now, as a little bit of an example, I always like to think about this as, I'm going to use an example. So this is called a weighted average. Now, to do a weighted average calculation, we're going to go on to the next slide. I got to get my calculator out, so just bear with me for a second. Okay, so let's think about, so this is all an example, or this is like a metaphor. I'm going to say an Oreo cookie is 2 wafers and 1 filling. Okay, would everyone agree with that? I think so. Now, let's say that you went to the grocery store and you picked up a party size thing of Oreo cookies. And in that, you had, let's say, 100 cookies. And you got those 100 cookies, and you determined the mass. You put each one of them on a digital balance. And let's say that 10 of them had a mass of, let's say 13.6 grams. I'm just going to come up with arbitrary numbers. Then 25 of them were 14.2. Then let's see, that gets us 65, or that's 35. Then we got 50 that were 13.2. And that gets us to 85. Let's say our last 15 were 15.1. Okay. Now, these different Oreos are all similar to isotopes. Okay. Now, I'm going to ask you the question and add it to the chat. Which one of these Oreos, or which mass, is most abundant? $13.2. Absolutely. Most abundant. Perfect. I love it. Okay. Now, what is the average mass of our Oreos? Now, let me ask you, this is a yes or no question. Can I calculate the average by adding 13.6, 14.2, 13.2, and 15.1, adding those up and dividing by 4? No. Perfect. That would not be right. Okay? Because there are 10 that have a mass of 13.6. There are 25 that are 14.2. There are 50 that are 13.2. And there are 15 that are 15.1. Okay? So if I wanted to calculate the average mass of Oreos, what I would do is I would take 13.6 and I would multiply it by, does anyone want to, what should I multiply that by? By 10. Perfect. Okay, we can work with that. 10. Then I would say 14.2 times what? 25. I multiply that by 25 because I got 25 that are 14.2. Then I'd go 13.2 times, what do I got? 50. And last but not least, 15.1 times 15. Perfect. Thank you. Okay, so here's what we've got. I'm going to come up with this. I'm going to come up with a number that's a sum of all these things. So 13.6 times 10 is 136 plus 14.2 times 25 is 355 plus 13.2 times 50 is 660 plus 15.1 times 15 is 226.5. Okay. So then I'm going to add 136 plus 355 plus 660 plus 226.5 equals 1,377.5. Those numbers, I came up with that number by taking the abundance, the number of each of these different masses, and multiplying them. So this 1,377.5 is my total mass of all 100 Oreos. Now, what would I do if I wanted to figure out the average mass of my Oreos of all 100. I divide it by 100 because this is my total mass. Okay, so I divide it by 100 because, no worries, good, I like it. Divide that by 100 because there's 100 Oreos. So my average Oreo mass is 13.775. Did everyone, can I get a thumbs up if that's followed? Okay, okay, great. Wonderful. Okay, so what this is really showing is that we have all of these different, the Oreos are similar to our different isotopes. These are 3 different isotopes of hydrogen. Are they all hydrogen? Yes, they are. They are all hydrogen. What differs is the number of neutrons. So what differs is the mass of them. If you went to the grocery store and you got this sleeve of 100 Oreos and you weighed each one of them individually, my question is, are they still Oreos? Yeah, they look like Oreos. They taste like Oreos. There's no doubt about that. But then the question is, okay, well, what makes them different from one another? Well, their masses are different from one another. So if I wanted to figure out the average mass of my Oreos, I would have to add up the mass of every single one of them. We're just kind of streamlining that and saying, well, 10 of the 100 are 13.6. 25 out of 100 are this. 50 of 100 and 15 of 100 are this mass. Now, another way of saying that is rather than saying 10 out of 100, what's another way that you could say 10 per 100? What's something that you come across somewhat regularly that if you have 100 of them, you have $1? Pennies. Another way of saying a penny is a cent. 10 per cent. So 10 out of these 100. So 10% of them are 13.6. 25%, 50%, and 15%. We're simply taking into account the abundance of each of these and the percentages of each of these so that we can come up with an overall mass and an overall average mass. Okay, so that is why we get, so if you look at this number, we came up with 13.775. That's different from every single one of these numbers. But it relates to the overall abundance of our masses. Our most abundant one had a mass of 13.2. Nope. Here what we get, palladium, for example, rats, Joel, stop doing that. Our mass is, our average mass is 106.42. That might mean that 52% of all of the palladium isotopes are 106, and that 48% are 107.4. That's where that number is coming from, where you consider the abundance and all of the masses of those isotopes and divide it by the total number of that isotope. Or in our case, with the Oreos, we divided it by 100. Okay, that's where I'm going to stop. I'm going to stop my recording right here.